So the IQ of the general population is known to be normally distributed about a mean value of 100. A teacher thinks that their class is above average intelligence. So the teacher randomly selects 16 students to complete an IQ test, and their results are included in this table below, noting that the average is 106.63 and standard deviation is 12.77. So we're asked to use a t-test in order to test this teacher's theory and see whether there's any evidence to back the claim. So let me just start by drawing ourselves a little picture of what we're actually kind of looking at. So what we know is that there's like the population of people generally, and we know that this general population has a mean value of 100 for the IQ. All right, so that would be our mu. Now the teacher has got a very small sample of this population, all right, which is a few people from within their class, and they've measured the IQ for them. So the sample, we can count it up. I think it's got 16 people in it, so that would be the n value. And we're given up here the pre-worked average and standard deviation, so we don't need to do that ourselves. You could if you wanted to. It would just be applying the average and standard deviation equations to this data set. So the average, we're going to call it x bar, okay, so that's the 106.63, and the standard deviation we're going to call s, okay, and that's the 12.77. Now, one thing that we aren't given in this question is the standard deviation of the population, okay? All that we really have access to is the standard deviation of the actual sample that we had. So this is the reason why we're going to use a t-test rather than a z-test for this question, okay? If we were given the population standard deviation, then you would be able to do a z-test, but since we're not, we're going to have to do a t-test, okay? And that uses the sample's standard deviation as a stand-in, I guess, since we don't have this other one. So, in order to go through this process, I guess the first thing that we're going to do is write out our hypotheses. So we have a null hypothesis and an alternate hypothesis. All right, so the null hypothesis, which we give the symbol HO, this is the hypothesis of no change or maintaining the status quo. All right, it's the boring one. So our kind of status quo would be that the sample of students has the same IQ as the population. Okay, it's the pretty boring conclusion. So we could write that as mu is equal to 100. Now the alternate is the more interesting one, and we give that H1, or sometimes people write HA for the symbol, and it's going to be kind of the opposite. All right, so that's going to be that the mu value is not equal to 100. All right, so now let's talk about the distribution that we're going to use. So our population is normal, all right, and if your population is normal for its distribution, that means that x bar, okay, is also normal. Now x bar, this is the sample mean, okay, so the distribution of the sample mean, so every time you take out, in this case it's going to be 16 people from the population, and you average them, okay, that's the distribution that you're making, okay, it's the distribution of the sample mean. So we should be able to describe this then with a mean and a standard deviation. And since we're using the sample as a stand-in, we're going to give it this symbol S, okay? So the distribution of sample mean, it should have the same mean as the actual population itself. So it should be distributed around a mean of 100. And then for the standard deviation of the sample means, this one is an equation we need to apply where it's equal to the S divided by square root n, okay, where S is this 12.77 and we divide by the number in the sample, okay, which is 16. So if you type that into a calculator, it comes to about 3.19. So all this is doing is kind of accounting for the fact that if you take a bigger number of observations into your sample, then you're going to have a less variance in the sample mean. All right, so that's all this is doing. So now that we've got that, we should be able to draw ourselves the distribution. So on this axis, I'm going to draw an x bar, which is our sample mean, and we've said it's a normal distribution, so it should have the bell curve shape. The mean is going to be this 100 value, so I'll pop that in. And I'll note off to the side here, the standard deviation is 3.19. Alright, so what we are looking for is any evidence of the teacher thinking that their students are actually much smarter than the general population. So this teacher ended up with an average of 106.63 for the mean of their sample. So if we mark that in, it's going to be, say, here. So what we're looking for is the probability of this happening, okay, or something more extreme. And if we find that there's a very, very small chance of this occurring or something more extreme, then that would suggest that we have strong evidence to suggest that the class is much smarter than the average population. So how we kind of make that decision is based on our level of significance. And back up in the question, we weren't really given any indication of what we should use for our level of significance. So in that case, I would suggest that you should default to 5%. Okay, so I'm going to write that in here. So I'm going to assume that our level of significance is 5%. So that's what our alpha value will be set to. Now, if we end up with a p-value which is greater than the alpha value, then this is going to be the boring outcome because we have insufficient evidence to reject HO. So that means we are just going to maintain the status quo in the context of this question. It means that this class has really got no statistical significance in terms of being smarter than the rest of the population. However, the other way, so if the p-value ends up being less than the alpha value, this is where we get the interesting outcome because we can reject HO and say, no, actually, we do have a class that is smarter than the average population. Alright, so all we need to do is figure out the area that's inside this section here, because that corresponds to the p-value. In other words, it's just the chance of this happening, alright, getting 106.63 or better by coincidence. So, how we're going to do this is applying our t-test. So we need to convert from being in x bar to being in t, and we have an equation for that. It's that very similar to the Z one, t is equal to x bar minus mu x bar over s x bar. So substituting in here, our x bar is this 106.63, our average is 100, and the standard deviation here is going to be 3.19. So if you pop that in a calculator, you end up with 2.08. So we're converting into the t side of things, so that means that this becomes 2.08, and if you convert your mean, it would end up going to 0 on the t-scale. Alright, so now we should be able to write out our probability statement. So what we're looking for is the probability that x bar ends up being greater than 106.63, and we've just said that that's going to be the same as looking at in t, the probability that t is greater than 2.08. The only other piece of information we need to be able to compute this is the number of degrees of freedom. So I'm going to mark that over to the side here. There's an equation for it, so degrees of freedom is equal to n minus 1, where n is the number in your sample. So if you remember right back at the beginning here, we said our sample contained 16 observations. So therefore, our number of degrees of freedom is 16 minus 1 or 15. Okay, so for your t distributions, it all depends on the number of degrees of freedom that you have. So I'm going to pop that in here. So I'm going to calculate this using Excel. So if I jump over, right, type in equals to start off your formula, and then if you type in t, it brings up a whole range of different ones. The one that I'm going to be interested in is this one here, which returns the right side of your distribution. If I just quickly go back here, you can see that indeed looking at this, I do want the right side of my distribution's probability. So all we've got to give it is, this is going to be our t-value that we're interested in, and ours is of course this 2.08. Okay, so I'll pop that in. And then we need to give it the number of degrees of freedom, which we just decided was 15. So this returns to me the p-value, so 0.0275. So let me pop that in here. And if I convert it to a decimal, it's about 2.75%. So that means there's, say, a 3% chance of me getting this result, or something more extreme from the average of my people in my sample. So the last step is just to decide whether that is significant or not. So if we go back to our section here, which was looking at our decision steps, so what we've ended up with is the p-value is less than our alpha value, okay, because we had 2.75%, which is going to be less than the 5%. So that means that we are going to reject HO, okay, and if I scroll back up, HO was that the mean of our sample was 100. So in fact, our mean is not 100, okay, so that means that the class is smarter than the general population. Alrighty, so that would be my answer to this question. So that's pretty much all there is in terms of this video.